a scientist from Japan. He studied lot about sound in terms of molecular. So we know that our body is comprises of 70% of water molecules. 70% of water molecules. So he studied about the sound, and he got Nobel Prize also. Means water reaction to the sound, right? Water reaction to the sound, and he created lot of sounds, and he carefully listened the water molecules through a microscope. Then he realized, he published paper also. Let's say, very good morning, it's a normal word. I like you all, it's a positive word. Then I don't want to spell that, I hate you, it's negative word, right? I don't want to spell any negative words. My basic fundamental principle. So if I say I like you all, then the water is reacted with a pattern, a unique pattern, look like a God's pattern. Look like very iconic pattern. I could tell you, it's look like a properly designed air bangles, and the properly designed look like a necklace, look like a diamond ring. If something I spell in terms of I dislike you, like no, the negative words. If I spell something, I hate you, I dislike you, then immediately the water molecules react with the word and shows look like a ghost image. If you spell a positive words, the water molecule react look like a god. If you spell the negative word, the water molecule reacts look like a ghost. So we know that our bodies comprises of more than 70% of the water molecules. My dear respected daughter, please listen to me. If you have any conversation, let me complete later. Fine? Please come. You got the point? So our bodies comprises of more than 70% of the water molecules. Sorry, I interrupted you. 70% of water molecules. If you think good thing, if you spell good word, கனவிலும் சரி நினைவிலும் சரி உள்ளம் மனசு எல்லாத்திலும் பாசிட்டிவா if you think you'll talk, then I'm sure it look like a battery. Myself look like a battery. Every minute, every second I'm charging with the energy. It could be a positive energy, it could be a negative energy. That's why I'll request you, I'll ask you to be silent. That will be more than anything what you have it in this world. I'm sure this world never gives you anything to you. Nothing. No, nothing is taken from here. Nothing. I cannot give anything because I am myself belongs to this world. So I don't have rights to give anything to you. So keep quiet, keep calm, keep silent, and I'm sure that silence will give you this much. If I cross after this word, this class will convert it into something, right? Look like a priest, right? I'm not a priest. I'm a simple ordinary person. So whenever I get into the class, I have all positive thought, right? I'm very eager to have you. I'm eager to see you and punch through some good words. Okay, fine. Now we'll get into the topic, right? Today we are going to have a common base configurations, like common base characteristics or characteristics of the common base configuration. So VI characteristics of common base configuration. So whenever you find, that too the first hour and after break, don't ask me permission. I know the reality. Please get it. I'll give you 100% permission because standing, listening me, and make me to, drag my attention is not your way. Just come. I'll allow you. Don't. Right now, we'll go inside the topic: common VI characteristics of common base configuration. And this class deals CB characteristics, and we also eager to learn early effect and some punch through right? Early effect is also called as early effect is also called as base width modulation, right? So possibly I cover these 3 points today, right? So VI characteristics. Okay, so what is transistor? Transfer signal from one port to another port. Transfer a weak signal from input port to output port. It is sometimes called as amplifier. If it is transfer, look like a transistor. If it is the process of conversion from weak signal into strong signal, then it is called amplifier. So there are roles and responsibilities of majority carrier as well as minority carrier, and I could call look like a majority carrier is role to perform a diffusion current. I could call the minority carrier is role to perform a drift current. In general definition, what is diffusion current? The diffusion current is the current conduction flow from higher concentrated charge carrier into lower concentration charge carrier. Right? What is diffusion current? Diffusion current is the current conduction. It is a current conduction, comma, the charge carriers flow from higher concentrated charges into lower concentrated charge carrier, right? Exponentially distributed. We know that, right? Exponentially. Let's say this is the simple piece of semiconductor. Let's forget about P and N. If the charge carrier look like higher, right? Here it is higher concentration, right? Higher. Let's assume always 100%. Here the lower concentration, let's say 1%. If the current conduction is diffusing from higher to lower, then this is called diffusion current. This is called diffusion current. Then what is called drift current? Let's say again there is a piece of semiconductor. Let's forget about N and P. If I'm going to apply some external voltage, due to applied external voltage, there will be a conduction inside the semiconductors called drift, and this is called diffusion, right? Diffusion, diffusion, drift, drift, drift. Okay. So this is in general, right? Now we'll get into the topic. We are eager to understand the common base characteristics. Why I'm getting into common base characteristics? Yesterday we had a hands-on experience over the common base inside the laboratory. So I like to insist CB on more than compared to C. Anyway, we are going to see C, but C is more important. Try to understand my words. It's important to you, right? Fine. Okay, okay. Now we'll get into it. So what is transistor? Transferring signal from one resistor into another resistor. So this is simple PNP transistor, right? PNP transistor. It has two depletion region: emitter, base, collector. So what is the role of emitter? Emitting majority carrier. I would say emitting majority carrier moving towards the junction. What is the role of collector? Collecting majority carrier. It is away from the junction. With respect to junction, I am calling towards and away. There are two junctions. Always, there are some common point in the transistor. You always remember that emitter emits, collector collects. When emitter emits, always when base emitter junction should be forward bias. It should support forward bias. To what? To diffuse. To what? To diffuse. Always collector has to collect, look like Dhoni, has to collect the ball. So always try to push the majority carrier away from the junction. Whereas here, pull the majority carrier towards the junction. So it always reverse bias. And I would say in generally drift current. Capital D, small d. Diffusion. So this we know it, right? This is electron direction, and I know the conventional current direction simply opposite to electron direction in the case of NPN. Again, why NPN always? Why NPN? So the NPN is you know the carrier, right? You understand, you try to understand what is electron and hole. Hole is the I would say it is a imaginary particle which is there, right, everywhere, but I couldn't feel it. Who is electron? Look like me. You can see, you can understand me, right? So that is one point. In most of the book, they given the mobility of the electron is faster compared to holes. Right? If I call you, this boy, he'll come very quickly. He'll call me. If I call him, he'll come quickly. Respond. Yes, what? Suppose I call somebody else in the neighbor, no, my last bench. Sometimes they couldn't feel my word and they may react lately. So I could call hole. I could call him as an electron. Hole and electron. Okay. So the mobility of the electron is always higher. So not only that, mobility. Okay. The gain of the NPN transfer is little higher compared to that. So that's why we always, even if you take any textbook, any book, it look like a local author to foreign author, any even standard book, will go always NPN transfer is taken for the understanding, derivation, and all those things, right? So this is a simple understanding, right? Look like understanding. Okay. So what happened this? What happened this? This is junction J1. This is junction J2. So junction J1 merely a forward bias. Merely a forward bias. Forward bias means you try to reduce the depletion region, right? So when I increase the forward bias voltage, then automatically the depletion region is always decreases. The point one. Point two, right? Always reverse bias. Why? Collector is nothing but a Dhoni. Emitter is nothing but a, to understand Virat Kohli or Kapil Dev, whatever, right? He's always a look like a batsman. He's always look like a fielder to catch the ball, right? So what is this responsible to collect? Right? What to collect? Majority current. It can be majority can be electron or can be a hole, right? So to collect, what to do? Collect it, right? What to do? Always reverse bias. Again, if you increase the reverse voltage, what happens? The depletion region increases. You try to understand this, then you will understand this, right? I'll tell you later, right? So junction increases. Okay, I'll draw one more diagram. One more diagram, roughly, right? One more diagram. This is N, P, N, right? Okay. So forget about this. Forget about this. Forward bias. Let me talk about the reverse bias. If I increase the reverse voltage, VR, then what happens? The depletion, the virtual line keep extending. Virtual line keep extending. Means the depletion region expand. Expand. Okay. Again, forget about this line. Let's say this line expanding. This line expanding. Because keep on increasing, this line expanding. This line expanding. Expanding. See, when I at zero, let's say this is at zero. So what is the depletion region? Depletion region at this point, this much. Means the base is maximum at zero. If I increase VR some level, right? Increase VR 1 volt. Let's say 1 volt. Then base start reducing. Start reducing. Let's say when VR at maximum, the base is almost touches to 0. Is that D or O? 0. Which means when base is reducing, what I am trying to say, when base is reducing, it reduces the recombination rate. In other words, the collector will increase the collector current, but other way, right? We forgot about these points. But remember, when keep on extending, then the effective base width is reducing. The effective base width look like reduce. Finally, the effective base width becomes 0, which means the emitter and collector directly short. Direct short between emitter and collector. Direct short, look like no base. Why no base? Physically there is a base. But electrically, we try to reduce and reduce to 0. That is called punched. This change in base with respect to applied voltage. Change in base width with respect to applied voltage called base width modulation. It is important to you. Early effect is important to you. Right? No doubt. So early effect. What is early effect? It is the effective base width of NPN transistor. Okay, it is the effective base width. right? It is effective base with, it is effective base with where, where, where the collector voltage or reverse voltage, where the collector voltage or reverse voltage keep on increasing, keep on increasing, keep on increasing, which results, which results decrease in, which results decrease in, which results decrease in, which results decrease in, decrease in effective base width of the transistor, decrease in effective base width of the transistor. It's called early effect. It's called early effect. EARLY, early effect. Next line. If it is keep on increasing, if it keep on increasing, if it is keep on increasing, comma, comma, the emitter and collector start, the emitter and collector start conducting directly. Emitter and collector start conducting directly. Or the effective base width becomes 0, or the effective base width becomes 0, comma, it is called, it is called internal short circuit between, it is called internal short, internal short between emitter and collector, internal short, SHORT, short between emitter and collector, or punch through, PUNCH, punch through, THROUGH, punch through, called punch through, which results, or it causes breakdown of the transistor. It causes breakdown of the transistor, breakdown of the transistor. Now come to the point. Now I want to take a common base, right? Base, emitter, collector. Now what is this? Listen, very important point. In the circuit manapadam pannadu, circuit manapadam pannadu, just follow me. Anytime you will have ability to derive and write, you don't need to read it, just listen. You got the point? Collecting, you got the point. Always, always base emitter form, always base emitter form, right? PN, positive. Got the point? Now what is this? This represents the conventional current direction. What is this? NPN. Okay, so according to NPN, emitter emitting electron, right? Electron has to go like this. Listen, electron has to go like this. Collector has to collect the electron. Emitter has to emit the electron, right? So when collector has to collect the electron, because electron is always a negatively charged, so I have to push positive voltage, right? Collect positive voltage, right? Attraction, right? When this emitter has to emit the electron, that I should supply the same voltage, which will repel the component and which will attract the component. So negative, right? Negative, right? Negative V. I'll tell you. Don't go. One by one. Negative. Got the point? Negative. What is this? Positive. Okay. What is this? Emitter, base, collector. So V, EB. Okay. So negative, positive. What is this? Negative, positive. Collector to base. So V, CB. What is the current? IC. What is the current? IC. What is the current? IE. Right? What is the current? IE. Any doubt in this? So now tell me, you don't need to memorize the positive, negative, those things, right? First draw the symbol, outward, arrow mark outward. Arrow mark shows the direction of the conventional current. Arrow shows the direction of the conventional current. The direction from collector to emitter. But electron majority look like, right? If it is a PNP transistor, then understand both electron, both the holes direction, because in PNP hole is the majority. In PNP hole is the majority. So conventional current direction there is same. Whereas here just focus. Right? Now we'll go one way. Shall I rub this? Okay, got the point, right? So I have teached you early effect, punch through, and diffusion and drift current. No doubt, right? Fine. Now let's we have a practical set, right? This is you understand, right? You understand this, right? Okay. Now we know that emitter is heavily doped, collector is moderately doped, base is slightly doped, and the base width is very thin. Base width is very thin with respect to base, with respect to emitter, with respect to collector. It is very thin. Now, usually, what we'll have some practical set, right? Shall I draw on that side? I'll draw it on the side. That's all right. Okay. Now this is an ideal circuit where I eliminate ohm meter, ammeter, voltmeter, ammeter, and resistor. Right? Why resistor? I've clearly told you voltmeter is stubborn, very strong. Internal impedance of the voltmeter is infinity. Right? Internal impedance of the voltmeter is always infinity. Why? It is connected across the positive, connected across. Whereas internal resistance of the ammeter is very less. Why it is series? Okay, that is one reason. But exact reason is that ammeter is what is the responsibility given for the ammeter? Ammeter is used to measure the current without disturbing the circuit conditions. Voltmeter, you got the point? Ammeter is series with the circuits. Ammeter is series with the circuit, right? Ammeter is, let's say, resistor 1 and resistor 2, right? Simple Ohm's law. Resistor 1, resistor 2, right? What is this? V is the voltage. Usually what we call current is same. But there is a voltage drop across V equal to V1 plus V2. Simple, right? Now, this place I put a ammeter. Then my ammeter should not take any voltage. What is V? This V equal to V. What is voltage drop across ammeter? Should be zero. Should be. Why? Because he is the monitor and supervisor, he is the instrument where what is the responsibility? Without disturbing the circuit condition, he has to follow the current, magnitude of the current. That is the responsibility given for ammeter. But instead, if he consumes something, right? If he consumes little bit voltage, then he is not a meter. That's why the internal resistance of the ammeter merely zero. So it is our responsibility to keep the ammeter safe. You got the point? So during Corona time, every doctors get into, I also there in the ward, right? Almost 15, 16 days. So I saw him, right? I mean, there are so many people, they, without care of themselves, they came near to me and did lot. Look like my mother, look like my God. Got the point? So it is our responsibility to keep the ammeter safe. Okay? It is our responsibility to keep the ammeter safe. For that, what I'm doing? I'm connecting a series resistance. I'm connecting a series resistance here. Right? Now we'll see a practical circuit. So the practical circuit comprises of Can put both the sides, not issue. So you want to take this, right? So what is emitter? Emit majority. Collector, mean emitter repels the charge, collector attract the charge of majority. Now we'll see the input characteristics of, now we'll see, this is the circuit diagram, right? This is common base configuration circuit diagram. The responsibility for the voltmeter is always used to measure the voltage drop across PN, and responsibility here measure the voltage drop across collector and base. This will record the IE value, and this will record the IC value, and this will record the voltage. Now the point is that, again we'll come to the point of understanding. There are 100 electron may start from here, and only 99 are reached. 100 is approximately equal to 99. Got the point? If 1 million electrons start flowing from emitter, there are double line electron are reached to collector. Because you know that, remember this point, get into your mind, please listen, get into your mind. Base is thin, base is lightly doped. Why? I have done it with a conscious way, right? I have done it in a conscious way. Why? Because he has to listen a weak voice. See, you got the point. We have a PM, we have a CM, we have a ministers, MLA. But why to come to down to the earth, look like a counselor, and the next by there are seat, and there are seat monitors, look like gone to the down level. Why? Because there are voice which may be hidden at the end. You got the point? So there are roles and responsibilities given from the top to down, which means lightly doped and very thin, which means the base is allows to listen weak signal. That's why that is the point of amplifier. What is amplifier? Listening weak signal. Got the point? Listening a weak in terms of micro millivolt, right? That's why it is very thin and lightly doped. So 100 electrons started and 99 have reached. So IE is approximately equal to 0.99 I. You got the point? Or here 1 million electron they started. 1 million electron started. That is the alpha electron reached, and 1 minus alpha retained in the base. Okay. So what is IC? Or in terms of IE is equal to IC plus IB, right? Because 99 and 1%. Okay. So this, just listen, right? Just keep it in the mind. Now come to the point of input characteristics. What is input characteristics says? Input characteristics says measuring IE versus VEB, right? Measuring IE versus VEB. Remember, I am using most of the time capital V, capital I, capital E, capital B, all capital. I'll tell you later why. Okay? Remember this, right? Capital IE, okay, in terms of milliamps and in terms of volts. And again, this is between N and P, between N and P. Look like a diode, right? So approximately here the voltage drop approximately look like 0.7. So I could use the voltmeter range from 0 to 1 volt. I could use the voltmeter range 0 to 1 volt. Now this is input characteristics. This is input characteristics. So I want to measure, or this plot or curve shows the relationship between input current and output current, right? Shows the relationship between, input current with respect to input voltage. What is that? Input characteristics shows the relationship between input current and input voltage. Input current represent IE, input voltage represent VEE. Okay. Then what about output? Output, I'm making this parameter constant, right? I'm making VCB of 5 volt and 10 volt and so on became constant, right? So at VCB is always constant, right? Now we'll listen. For example, I kept 5 volt, right? Now what is the voltage here? Exactly 5 volt. At 5 volt, what happened? I start increasing from 0 to, as I mentioned, so the maximum range is 1 volt, right? 0, zero point 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. So before this 0.7, see the 0.7 is not a universal value. Remember this point first of all, right? Theoretically saying everybody, every book lies you, even me. Why? 0.7 is not fixed. I'm lying to you. Why? Because exactly if you go and check trillions of transistors, take trillions of transistors, measure it. I'm sure all trillions of transistors having its own unique barrier potential, which means not equal to 0.7. Got the point? If I check 1 trillion transistor, that's my responsibility today. I have to check and report. I'm checking 1 trillion transistor. The measure VBE theoretically says that every standard, even God will come and say 2.7. But if you measure it, I am sure there will be change between 0.65 to 0.712. See, if you take more number of digits, 5 digits, I am sure it's not at all equal. If it is equal, this is not a it's not a silicon, or it's not belongs to it's not a real fact, right? What I'm trying to say, right? Got the point? It is impossible. Some of the point is impossible. There are 736 crore people are living. All are different retina. Retina is different. Got the point? Now look like I'm saying 0.7. It's not ideal, right? 0.7 means here and there, right? So almost 0.7, there is a barrier potential. Almost 0.7, there is a barrier potential. So the barrier potential is look like P and N. So barrier potential from here it is maximum, from here it is minimum. I'll draw two diagrams, don't worry. Exactly at this point, the depletion region is look like. The depletion region is look like exactly at this point, right? When I keep on increasing the voltage, so there is a minority carrier. Always there is a minority carrier, because listen, I'm raising this potential. So automatically, if what happens when I'm raising it, what happens? This dr keep reducing. This dr keep reducing when VEB rising. Okay, so what it means? Diffusion, drift current, right? So when keep on increasing, exactly at this point, the diagram is look like this. Right? The diagram is look like this. Exactly at the barrier potential, exactly at equal at potential, the barrier potential is approximately equal to 0. Mean no barrier, no gate. Mean we can easily access our road, right? No toll booth, no collection. So it means it's a direct path between P and N, but there is a marginable line is always put marginable line, because it is implanted, boron implanted, and this is arsenic implanted, right? You got the point, always marginable. Mean I'm saying that there is no barrier, but don't forget to draw a line, right? Always have a small line, right? Which will be the ethical way, right? So after this, my I is exponentially varying. E to the power of Vc divided by lambda Vt minus 1. Exponentially varying. Why exponentially? No barrier. You see that? At this point, no barrier. Right? What is that? Barrier potential almost equal to 0.7, but barrier depletion region. I'm sorry. The depletion region is almost reduced to 0 level. 0 level. But again, there is a virtual line is always there. Right? So this is for 5 volt. Right? This is at 5 volts. Now, I kept my output voltage 10. Right? Now for 10 means what is? Listen, what is base emitter? Base emitter is always forward bias. Base emitter is always irrespective of the configuration, common emitter, common base, common collector, irrespective of the connection given, always, this is constant. What? Base emitter is forward bias. Irrespective of the NPN, irrespective of the PNP, irrespective of what condition, any condition. Okay. What is collector base junction means? Output junction always reverse bias. So remember, what I'm increasing, if I'm increasing 10 volt, if I'm increasing 10 volt, I am increasing the reverse bias voltage. Increasing reverse bias voltage, which will attract lot of component, right? Which will attract lot of component. Got the point? What is collector? Collector has to collect. What do you mean by that? If I kept 5 volt, I'll attract. If I kept 10 volt, I'll attract more. I attract more negatively charged particle because attraction. What does it mean? Positive volt, right? So if I kept 10 volt, I attract more, which means IC tends to increase, right? IC merely tends to increase. When IC tends to increase, what is IC? What is IC? What is IC? Without IE, you cannot climb IC. Without IE, you cannot climb IE. Without IE, you cannot climb IC. Got the point? What is IC? Bowler ball போட்டா நம்ம catch படிக்க முடியும். Got the point? So collector current is always depends 100%, 200% depends. Okay, so that's why what is that? Out reverse voltage increases, so the current is increased, right? Right? Milliamps, 3.5 milliamps with respect to this exact value, right? Exact value. Got the point? What is the input characteristics? You understand or not? You understand or not? Yes, you got it? So, if I increase this, I will try to mean now. Fast bowler ku udoni enga irupar pinadi irupar in a fast ball, right? Spin ku enga irupanga? No, and exactly just behind the stumps. Swing ku, in between that. Got the point? Yes or no? Look like, see, I'm not taking something else. I'm taking which is relevant to me. It's relevant to conceptual clarity, right? That's why you're calling you, right? The big man name, right? Okay. So So if I increase, what happened? The collection, it will come forward, or it will assume whatever, right? So it will try to increase the depletion region. So this depletion region, exactly at this point, it becomes zero. Exactly at this point, it becomes, right? So when it becomes zero, current exponentially varies. Look like a skyrocketing. Look like skyrocketing. Got the point? What I'm trying to say? Yes, this is input characteristics. Let's see, move on to output characteristics. Now, get ready. Shall I rub this? You want to take this? I'm sure this graph, which may be available in the book in a different form, even if you ask me to the next class, I'll draw the same graph with a different explanation. Right? That's why I'm asking you to record it. Got the point? Yes. But the value is exact. I didn't change this. Okay? With respect to some. The place quick. Okay. Shall I rub this side for the output characteristics? Got the early effect, punch through. We'll see what is the early effect and punch through. Okay, same diagram at IE constant, right? What is output characteristics? Output characteristics at IE, right? Constant. What is IE? Input current. Okay, now the graph. This is the current axis always. This is the voltage axis. This is, yes, my dear students, this output, right? This collector current, this output voltage, collector to base voltage, right? So collector current, right? Collector current is also milliamps. Collector current is also milliamps, and again collector to base voltage. Okay, collector to base voltage. But here the responsibility is that is responsible to attract the majority current, hold the majority, attract. So always remember that for input, 0.7 is enough. Anything more than 0.7 is enough. Will easily make the forward bias. Why? Emitter is heavily doped. Emitter is, see, always you have a ability to correlate all the information in the right form. Then only the sambar will come out. You got the point? If you missed out salt, if you missed out something else, the taste of the sambar will move in a wrong way. Look like, why this become 0.7 or 0 to 1 volt? Why this become 0 to 30 volt? Because moderately doped. huge area, right? Emitter, base, collector. You see that the width of the collector is extend, keep it moderately doped, whereas very specific, highly doped. Specific, highly doped. Base is very, very lightly doped. And why lightly and then the base responsible has to listen a weak signal, mic, right? Mic signal, weak signal. Responsibility of the listening are microamps. And responsibilities of converting microampere into milliampere. Take a common emitter configuration. Microampere base, right? Which is connected directly to the mic. Collector milliamps directly connected to the speaker, right? Hearing, right? Decibels, right? So micro to milli, 1000 times amplification. Micro to milli. Why micro? Lightly doped. That's why I consciously made thin, lightly doped. Why? To listen weak ones. To listen weak ones. And to produce strong. Why? Strong emitter is heavily doped to produce strong amplification. Moderately doped collector to support strong modification. Got the point? What is emitter? To produce strong modulation. What is collector? To support strong modulation. Support to go, create to go. Emitter is a creator, look like a Brahma. Right? What is collector? Look like a Vishnu. What is base? Look like recombination. Angandu kalamanama ange poyi ukarum. Losing energy. So 100, 99, 1. Kadasi bench la kada sonna kuda gavanikala na nanappu. Very interestingly talking something. I'm very happy to listen to you. Why? You have very interesting topic than me. If you really have interesting topic, those who are talking there in my forum, please come forward. I'll give you dias and time for you. I'm sure I'll switch off my mic. I'll give you dias to you. Please chit chat something, look like a joke or information, scientific evidence, whatever, right? You look like. Please come forward and deliver your instance. Thus, my instance always very intent to listen. Listen you, not listening. I'm listening. Why? You are my all, right? You are my student. I like you very much. Okay, so please follow me, right? Okay, now output characteristics. For the time attendance next class. Now output characteristics. See, keep, yeah. This is my instance, right? Always 3 minutes.